that you're in your car. Love you too. So is there an easy way to ask, can everybody hear me? Is an easy way to ask. Is there an easy way to get an answer? I see a bunch of thumbs up. That's excellent. We're very close to everybody, just going by number of participants. So did everybody, you guys are able to unmute yourselves, I think. Did everybody find the lecture videos, the pre-lecture videos?
Yes.
There, hey, oh, excellent. Great. So if you're having, I mean, you ought to be able to find me because using speaker view. I was gonna say I'm the bald guy with a beard, but Josh.
Yes.
Yeah, and that's great. So I'm the bald guy with a beard with Iron Man mask in the background. That's certainly a child's toy that I found at Goodwill long ago. So seems to be 6 o'clock. So let's do a couple things. Let me welcome you to Physics Physics 1, General Physics 1. I did do a syllabus video, so I'm not going to go through the syllabus right now. Mostly because I need to end today's lecture 10 minutes early because I have another Zoom meeting to go to at 6:30. So I'm going to end at 6:30 and log on to another Zoom meeting. It's a good time. Also, I have 3 monitors in front of me, and that doesn't seem to be enough, but that's going to be okay. Okay, so what do I want to do? Let's do this. Canvas is going to be where you'll find most of what you need for this course. I'm not planning to send email blasts to everybody often, unless it seems like super necessary. I'll mostly just post announcements. The pre-lecture videos I am going to put on a page of the of Canvas. See, now I've got too many monitors. There. There'll be a link to that page from the front page, right? So the front page has all the Zoom link pages links. Does that make sense? I'll put that that list there. Also, a couple of you have subscribed to the YouTube channel that are these videos. That reminds me, I intend to record this. Oh, it's recording right now. Spectacular. Okay. Let's just dive in. Let's just dive in. Let me make sure. If you guys have questions, what should you do? I don't know. I mean, somebody ask a question. Beth, ask me a question.
Can we type them into chat?
Oh, there we go.
You can, but then I have to watch the chat.
You want,
Beth said hi.
this is Beth. Matt, do you want me to watch the chat for you?
Oh, sure. Yeah, that'd be great.
That'd be easier. They can just type questions in the chat.
Yeah, if you want to.
Okay, I can do that for today.
Fabulous. Okay, this is going to be great, you guys. So I'm going to. This is going to be. Let's see if this works. I'm going to share screen 3, which is a screen mirror of the iPad. Look at that. So you all can see that, right?
Mm-hmm.
Yes.
Yep.
Okay, so what I didn't do in the pre-lecture videos is answer the question that every intro course asks. What is insert topic here, right? What is physics? What is sociology? What is biology? So I'll answer that question as succinctly as I can, partially for time, but also because I don't know. What is physics? I don't know. You're going to find out in the next course or two if you're signed up for both of them. So mostly we're studying the physical world, right? With an eye toward describing it as simply as possible, right? Maybe finding some fundamental rules that govern what happens in the world. The thing that makes physics different than, say, other sciences. So chemistry, you can say the same thing, but it's very specified to a specific scale, right? Atoms and collections of atoms. For biology, it would be collections of lots of atoms, maybe from the scale of a single cell to an entire planet, right? Our planet specifically. For physics, though, our scale is all of it. All of it. So everything down to subatomic particles, right, and the femtometer range, up to the size of the universe, right, the 10 to the 20, 10 to the 25. I don't know, that seems like a big range, right? 5 orders of magnitude, but at that scale, that 5 isn't a big deal. Okay, so I talked about a couple of these things. I talked about SI units. I think I talked about scalars and vectors a bit, right? So what's the difference? A scalar is is just a number, and a vector is not complete without direction, right? And we have these three basic things that we can measure, which are length, time, and mass, right? And mass is kind of a quantification of amount of things, right? Amount of stuff. So let's see, what do I want to say about that? Most of the other quantities that we'll talk about in this course in particular are derived from those three things, all right? I think I said this in the video. If you take a length per unit time, that's a velocity, right? If you take, let's see, a mass times a length, see, I'm wasting time. That's okay. I like to do this though. If you take a mass times a length per unit time squared, that's a force. And you wouldn't necessarily know that off the top of your head. Right? I had to even think about it. But we'll build that as we get to it. Okay. So what I want to do first, I guess, is one of these. Come on, you can do it. One of these that I didn't do in the pre-lecture video. So you can all see this 27 or 2.7 grams per cubic centimeter. Fabulous. Okay, let's make that go away. So let's do this last conversion. As I did in the video, I like to put the fraction, instead of inline, I like to put it top and bottom, right? Upstairs and downstairs. And then we need some conversion factors. So we need to go from grams, let's do this, from grams to kilograms, because kilogram is the SI unit. It's the only, as soon as you make a statement like this, you're wrong. It's the only SI unit, to my knowledge, that has a metric prefix in it, right? The rest of them, so kilometer is not an SI unit, it's the meter, right? But the gram is not an SI unit, it's the kilogram. And that probably has to do with scale. A kilogram is more of a lab scale quantity. And we want to take cubic centimeters, we want to make that meters. All right, so it looks like these are just going to be powers of 10. And that's the beauty of the SI system, is changing scale is a simple matter of powers of 10, whereas changing from feet to miles, you have to remember an obscure number, right? 5,280, which I know, but you know, if I grew up in another country, I wouldn't. That's okay. So we're going to multiply by 1 a couple times, several times, right? And in fact, you may have seen this in the past this way. Often chemists do this, and that's fine. I'm not going to. But if you want to use this kind of setup to multiply by fractions, that is totally okay. I'm going to make it look a little more mathy and do this. So the conversion factor for grams to kilograms, I remember a conversion factor is just an equality. So I could say, I need a number. Come on, I really just want, nope, go away. I want an equality. So I want something that relates a number of grams to a number of kilograms. And I can remember that kilo here means 1,000. That K literally means 1,000. And in fact, I can go to conversion factors and metric prefixes. I have that here, right? Like, oh, here, it actually says kilo here is 10 to the 3. By the by, I have an equation sheet for all of our exams that I will post so that you can look at them now, so you can have those equation sheets while you're working homework. Okay, go back. Yeah, that's because I'm not paying for that app. Okay, so that K means 1,000. So I'm just going to replace the K with 1,000. That's pretty simple. So that's 1 gram is 1,000 kilograms. That's mostly legible. And I want the grams to go away. So I'm going to put grams downstairs and kilograms upstairs. And it's 1,000. Oh, you know what? You guys, no one flagged this? No one said, hey, that seems like that's wrong. Should be 1 kilogram is 1,000 grams. I replaced the K with a 1,000. Boom, right there. So I'm not immune to mistakes. But the last step of any problem, right, this included, is does my answer make sense? And this mid step here didn't make sense when it was 1 gram equals 1,000 kilograms. That was definitely wrong. Okay, so it's 1 kilogram is 1,000 grams. Awesome. All right, and I'm gonna make that go away so I have a little more space. So that makes the grams go away, and I'm left with kilograms. So I need cubic centimeters to go to cubic meters. So I'll multiply by another fraction. Centimeters is downstairs, and I want it to go away, so centimeters goes upstairs, and I want meters to show up downstairs. So I can look up the equality, right? But really, I just need to fill it in this this fraction, right? So what is it? It's 100 centimeters per meter. So here, and I think I said this in the video, I didn't replace centi with 10 to the minus 2. I could have. I could have said 1 centimeter equals 10 to the minus 2 meters, and that would give me the same fraction. It wouldn't look exactly like this, but it would give me the same result. But I think this is easier to think about. Okay, and that makes centimeters go away, but it only makes one of them go away. So I need 3 of these, and that'll give me kilograms per cubic meter. All right, so all told, that looks like I'm dividing by 1,000 and then multiplying by 100 3 times. So that's 10 to the 6 divided by 10 to the 3. So this should just be 10 to the 3 on top of this 2.7, which is 2,700 kilograms per cubic meter. And I like to do this example because it gives us a ready conversion for this. This is a density, right? Mass per unit volume is a density. And this gives us a good sense of, for the SI unit for density, it should be kilograms per cubic meter. But I've never seen a cubic meter of aluminum, at least not in a cube, right? I've probably seen that volume, right? But it's been, I don't know, something else that was made out of aluminum. But a cubic centimeter of aluminum I've seen, right? Because I taught physics labs that have cubic centimeters of aluminum. So the 2.7 grams per cubic centimeter, that's actually a better lab scale for this number. Okay, so let me ask, are there questions? How are you guys doing? Things are good. Oh, yes, the thumbs up. The emoji and all. Okay, so let's move forward. So I did a video on sig figs. Let me tell you, I'm not gonna harp on sig figs very much past the first chapter, honestly. I think there are a couple homework problems on it. It's useful to be aware of them, but I'm an experimental physicist, so sig figs are not a thing that I worry too much about because everything I do has experimental error on it, and the sig figs are not super necessary. So I propagate experimental error through things, and that's always bigger than the sig figs would govern because I build terrible solar cells. So it's good though, it's fine that they're terrible. I'm not trying to set records, I'm just trying to make new things. So that's that. It's good to be aware of sig figs. So let's move forward. The next thing, so that's chapter 1. We're done with chapter 1. The next thing was chapter 2. And let me, do I have chapter 2 scratch work? Yeah, this is pretty much chapter 2 scratch work. So I defined displacement, right, as a delta x. Yeah, we're doing pretty good. Let me, so displacement is a vector, right? It's an arrow from where you started to where you end, right? Or if it's not you doing the moving, it's something else. So let me just do an example. So this is example number, come on. I want to edit, there we go. This is example number 2, I think. No, it is not. It's example number 3. I'll go back to example number 2 in the next bit. So example number 3 says Bob walks 2 kilometers north and then walks 1.4 kilometers east, and I want to find his displacement. Okay. So this seems pretty straightforward. There was something I was going to say right then. What was I going to say? Oh, this lecture handout is posted on Canvas, right? So the blank version and solutions that I've worked a number of years ago and posted. Okay, so the first step for almost every physics problem is to draw a picture. So I'm going to draw Bob. Bob has more hair than I do. That's great. And Bob walked 2 kilometers north, so I'm going to draw an arrow north. I'll label it 2 kilometers. And then he walked 1.4 kilometers east. So east is to the right, unless we're looking up, I guess. So that's 1.4. That's, you know, shorter. Great. 1.4 kilometers. And I want to know his displacement. So part of the reason I'm working this problem is I want to make the distinction between displacement and path length. Right? His path length is 3.4 kilometers, right? If you drove this in a car, your odometer would tick 3.4 kilometers. It would say it in miles probably, but it would literally tick that far. But displacement is final position minus initial position. Displacement is, let's do, I don't know, purple. Great. Displacement is this arrow. That's what I want to know. Right, that's my delta x. So how do I go from what I know, right, 2 kilometers north and 1.4 kilometers east to that delta x? Anybody? Vanessa said it, but you're muted. No, you're fine.
Isn't that the Pythagorean theorem?
That's it, yes. Pythagorean theorem, a squared plus b squared equals c squared, right? How do we know? Because this is a right triangle, right? If it weren't a right triangle, we'd have to do something a little more complicated, which we will talk about when we talk about vectors in chapter 3. Yeah, so a squared plus b squared equals c squared. So this guy's a, this guy's b, and the hypotenuse is c, right? So delta x is the square, we'll just say delta x squared, is 2 squared plus 1.4 squared, right? And then we could just, here's how I would plug it into my calculator. I would do all of this raised to the 1/2, right? Because raising something to the 1/2 is the same as a square root. If you're uncomfortable with that, do it however you're comfortable. It's totally fine. So, no. Can you guys see that little pop-up?
Mm-hmm. Yeah.
I will be clicking maybe later a lot. So, where is that answer? Where are you, buddy? There, 2.44 kilometers. 2.4, oh, that's not looking. I'm not going to replace it with a better looking for, but there, okay. Great. Anyone know how I would find this angle?
I mean, couldn't you use sine or cosine?
Yep, sine or cosine or even tangent at this point. Actually, we could have used tangent before. So do we remember those things? I think I put that over here. Oh, no, I didn't. I downloaded a reminder of, okay, well, that's fine. I probably have that tab up. I won't let you guys see, but I've got like probably 30 tabs open, and that's like modest for me. So yeah, sine, cosine, and tangent. You guys remember this stuff? SOHCAHTOA. If you haven't seen this before, this is going to be a useful thing for us to remember. I will post this thing. Although honestly, if you just Google trig functions, this will show up. So it's just a way to relate the sides of triangles. So by the way, you're going to want a calculator that lets you compute sine and cosine, or arc sine and arc cosine, because that's what we would need for this one, is an arc one of these. Since we know all three sides, we can do any one of them. Okay, I'm not going to belabor that because we're going to do plenty of that in the future. Go back. Okay. Great. So what else did we talk about? Let's see. We talked about motion diagrams. That was in the pre-lecture videos, right? A motion diagram is just a way of representing motion, right? Kind of like points along the way, right? We're using this point mass approximation where we're drawing the child on a bike as a point. And we will continue to use a point until a point is not sufficient to model the problem, right? One of our approaches to physics problems and to physics in general is to simplify everything as far as you can without losing important information, right? So I don't lose anything important by reducing the child on the bike to a point. That's in a very physicsy sense and not in a interpersonal sense. The child and the bike are very important. Case in point, my 5-year-old used to ride a bike that the chain came off, like probably every 100 feet we would ride. No, that's too far. It was more like every 10 feet. And then we found a bike that someone had put on the side of the road. Yes, so I got my daughter a Hello Kitty bike from the trash. It wasn't in the trash, it was next to, probably not doing a whole lot for anyway, it's a much better bike. And even if she were on the Hello Kitty bike or the bike that the chain fell off, they would both be a point. But the motion diagrams would look very different. I digress. That's a character fault. Okay, so let's finish this. I want to talk about this very last motion diagram, right? The student walking to class. It says that she started at a medium pace, she slows down, and then she goes fast. And in the video, I finished before I was able to do example 2, which is calculate the average velocity in each of those ranges. I think I mentioned I have 3 velocities here, but I would like to calculate them, right? We call it V1, V2, and V3, right? So we've got this equation for velocity. It's great. The equation for velocity, right, as trying to write with an eraser, V is delta x over delta t. But I want to highlight the fact that that's really for an average over that time and that distance, right? So this is very important because tomorrow, when we finish chapter 2, is that tomorrow? Good grief. When we finish chapter 2 tomorrow, I'll talk about acceleration, which is a changing velocity. And if you use this equation to find positions given a velocity at some point, if that velocity is changing, this equation won't work anymore. I also want to do one other thing to this equation, which is this x final minus x initial over, leave that over delta t. I can rearrange this equation. I can multiply by the delta t. I can multiply that over here and then add this guy over to the other side, and I get another equation, which is x final equals x initial plus v initial delta t. This is a useful equation for uniform motion. And you'll see in the, in the lecture videos, the pre-lecture videos, I've started this list of equations. This is our single solitary equation under constant velocity motion. Once we get to constant acceleration, we need to modify this equation with another term. All right, So what I'm saying is this: if you use this equation for not constant velocity motion, you will get a wrong answer, right? So just because there is an equation that relates things, you need to know that you can't just use it willy-nilly, right? You've got who says willy-nilly? I don't think I've said willy-nilly for years. Okay, oh, that's fine. Okay, I guess that's part of me now. So let's finish this guy. So I finished my previous classes, right? Switching to recording lecture videos, as did, you know, the rest of the world. And is this where I'm going to get right here? What I missed from it was feedback. What I liked about it was I could correct mistakes. So this removes, actually it adds in the reduced feedback, but it removes the ability to correct my mistakes. So I'm having a fun time. So I want to make most of this go away because this was more of a reminder slash introduction, right? So average velocity, that's what we're looking for these two examples. All right, so I'll set that off to the side because I'd like to use it. So the average velocity in example 1A, I've got 4 minutes. I can do this. So how do I find average? Well, if we assume that the motion is constant, it's uniform, then I can use any region in here, right? I could use, this is what I want. I could use these 2 points, right? I could use these 2 points. I could use these 2 points. You see what I'm saying? So I think what I'm going to do is use the entire motion, right? And what that does for me is it makes the math a little easier. Not that it's hard, but it's, so V average, again, is delta X over delta T. Delta T for the first one, what was it? 3 minutes, and it's 100 meters, right? So it's 3 minutes and 100 meters. So X final is 100 meters and X initial is 0 meters. So 100 divided by 3 is 33.3333 meters per minute, which is not an SI unit. So we could multiply this by 60 to get meters per, or sorry, divided by 60 to get meters per second. Also, this is one of the examples where sig figs come in handy, except how many sig figs does this 100 have? 1, the way it's written. So do I really want to keep just 1? Well, we could assume those other 2 are 0. This is what makes making exams a little difficult. So I try not to use round numbers just so there's no ambiguity about sig figs. So I would have made this probably like 125 meters just so there was no ambiguity. As it is, I'm going to get rid of probably that. Maybe add another. I will add that last 3. Maybe later. I have no intention of paying for that, so I feel a little dishonest clicking maybe later. If they had a no thank you, that would be probably the best case scenario. Okay, so let's do this last one. I think we'll be good, guys. The V average for the last one, it's the same idea, right? Delta X over delta T. I think that you can follow that. So rather than have you watch me for another 2 minutes, scratch away at this iPad, let me ask you guys, what questions do you have? We've got a couple minutes. Are there any questions?
On the homework that you have assigned on WebAssign, you specify what problems you want us to use significant figures on versus not?
It does, yeah. I think there are, in the very first homework, there are a couple of problems that actually say how many sig figs are in this number, or do this math with the proper sig figs. But past that, I think I set it not to worry about sig figs.
Okay.
That's an excellent question, though, because yeah, I could set it to be very strict, but I don't want you worrying about that. I want you worrying about other things.
There was
Other
a question about whether or not you're going to post the video when it's done. There's some connection problems people are having.
Yes, I will post this video when it's done. It probably won't show up tonight. It'll probably show up tomorrow. But yeah, I'll post this video. Because all of my awkwardness needs to be preserved for posterity. Yeah. Okay. Other questions? Last call. Great. Okay, so
Yeah.
I did post. Yeah, Chris.
What do you use to shave your head? I'm a Gillette guy.
Yeah, so I used a Flex 5. Oh, what is it? I think it's a Bic.
It's a
Before
Bic?
that, I used something that that nicked up my head terribly. I used it for probably a year. It was awful.
Stay away from safety razors, man. And electric's no good either.
Yes, the safety razor. I thought, oh, this is going to be great.
Yeah.
I got it. It was a gift from my wife, so I used it for a long time. It was terrible. I bled a lot. Okay.
Well, she might have enjoyed that at a later date.
It's possible. Okay. All right. So I'm excited, guys. I will see you guys tomorrow at 6 Eastern. I don't know where you are, but I know where I am, which is the basement with Spider-Man over there and Iron Man over here and Pez over there. I'll show you someday the Pez on the wall over there. Okay. So I'll see you guys tomorrow. Thanks for coming.
Thank you.
Okay.
Thanks.